Hello everyone. So if you remember last time we were going through the Bayesian rule, we went back through the to review probabilities, basics, and so on. And now we are going to move to the Bayesian networks. Okay. So we were starting last time here. We were talking about this professor, Julia Pearl, if I'm pronouncing his name correct. So this inspiring person was really motivating us last time when we were saying that we watched a video for this person. We were also I was sharing with you the website where you can find more information about his achievement and so on. And one of his biggest achievements is he was utilizing the Bayesian networks and the causal inference for winning the Turing Award in 2011. Okay, so this could only inspire all of us, and let us focus more with the Bayesian networks. So how did we move from the simple rules to the Bayesian networks? So this is what we are going to explore together. If we are going to start our discussion about the joint distribution. And here, joint distribution, so if we have this example, we were going through probabilities. So if we know the joint distribution of all the probabilities, we can answer any question given whatever the domain we are focusing on. If I know the probabilities of every single variable, with which exact value is going to take place or not, so we can decide about the whole space, okay? So in this case, if I have, in this example, big X is a random variable, and it's having a set of x1 to xn, the probability, or let me say the joint probability, because last time we said that this comma between x1, x2 until xn, we read it like the probability of x1 and x2 and xn. Okay, so the probability for this, for the joint distribution, could be found each time we are going to consider then that one of the variables, first of all variables are there with the value true. Each time there could be the negation of one of the given little x's, okay? So we end up having the negation of all existing variables. So to sum up all this, we have huge, it depends on n. It depends on how many variables in total we have, okay? If, for example, you are going to have 3, you are going to sum P1 plus P2 plus P3. And each time, no matter how many variables you have, what we know, given a specific domain or distribution, the sum of all probabilities must be equal to 1, okay? So what we can see here, if the number of probabilities is little, it's okay to sum up that. But imagine with me that here we have too many variables, and this n is going to be huge. So what could happen in that case? We are in the case of Bayesian network. So we are talking about a lot of variables. In this case, I am going to illustrate the concept with a very simple Bayesian network, but it is really could handle more complex situation, and this is what we are going to see today. Okay, so a Bayesian network, if we go through its definition, so it is a data structure to represent the dependencies or independencies among variables. And when we see variables, for example, I have here 3 variables, and here also I have the same 3 variables, but the dependencies and independencies are different. Here, for example, I can see y here depends from x, z depends from x, and here it's the opposite. It's x who depends upon from both y and z. If we see x here, it's an independent variable. Here, which are the independent variables? They are y and z. How you can guess this? If you have the arrow is entering, you have inputs means this variable is not independent. It depends from something else, from where this input is coming. If you don't have any inputs, then this is an independent variable, okay? And here, so we are going to use the independence, and this can reduce the number of parameters for joint distribution. We are going to illustrate that with like examples, and you are going to be able today to learn how to compute the number of parameters in both cases of joint like distribution and the Bayesian network. And we are going to see the difference, okay? So here, for example, if you want to compute the probability, the joint like distribution means the probability of X and Y and Z. It's equal to the probability of X. Here we see that X is independent. It doesn't depend from anything. And this is why you consider here that you are having a probability of X. Okay. And next, we have the variable Y here. It depends upon from X. This is why here you have the probability of Y given X. And also for Z, so how to compute this? This is the conditional probability, which gives probability of Z given X. So the joint probability here is the multiplication of each of the probabilities, how it's going to be computed. Is that clear for everyone online?
Yep. Yeah.
Okay, so we try to like see the second example where we are doing the same thing. We are computing the probability of X, Y, and Z. And in this case, each time you need to pay attention to the graph. So in this graph, what we have, I check which are my independent variables, which are Y and Z. So here I have the probability of Y given like nothing, and I'm not going to consider any conditions, okay? The probability of Z, and for X, which here depends from two variables, so we consider probability of X given both Y and Z. Is that clear? So now if I'm going to give you any graph, you are able to write like the joint probabilities for this graph, okay? Okay. So this is a very simple case. If we move now for a more complex example, we went through this example last time, if you guys remember. So here we have the alarm, and if there is an alarm, means there is like whether an earthquake or a burglary, and if there is an alarm, then like maybe Mary calls or John calls. Okay, so we have this graph. You always pay attention to the like rows where like we have the like entering or like to guess which variable is depending from which other variable. Okay, so first thing, if you are given such an example, the first thing is you try to give a notation for each of your variables. So you extract all your binary discrete variables. So in this example, we denote by B the burglary, E for the earthquake, A for the alarm, M for Mary calls, and J for John calls. Okay, so we have our binary discrete variables are B, E, A, M, and J. Okay, next, now what we are going to see, we are going kind of translating this graph to probability language. So I am going to express here B. Is it depending from something? I would say no. So the probability of B just is the probability of B. It's not a conditional probability. Same for E. So here we have the probability of E. And next, the probability of A. Here it depends from both B and E. So we write probability of A given B and E. Same for M, depends from A. So we have here the probability of M given A. And here the probability of G given A. Okay, so now we are able, first of all, to define our set of variables. Then we are able to give each like arc, each like notation we are going to translate in probabilities. And now what we need to do is to compute the joint probabilities of all this. Means I want to compute the probability of B and E and A and M and G. It's the whole like space, okay? So the probability of all this. So each time something, as we are saying, we are dealing with uncertainty. Means I'm not sure if this will happen or this will happen. And when I say this will happen, means this takes the value true, means B. probably this will not happen, which makes us think of not B. Okay, same for E. There could be a scenario where we have E, it's happening an earthquake, and another scenario when we are talking about not E. For each of these like variables, you have the variables, okay? And each time we could consider the scenario when one of them is like false, means not one of the variables, okay? Until we reach to the probability like none of them is there, okay? There is no alarm, there is no one is calling, and there is like no events happening, okay? So in order to compute the joint probabilities, we need to think seriously about all these like possible probabilities. And always we keep in mind that the sum of these all probabilities is equal to 1. This is our deal from the start, okay? Now, in order to do this, there is a huge number of parameters. So, key concept here, if you have a set of independent like variables like this, and you want to compute the probabilities, there is a rule that we seen last time. And the rule says that, who is remembering this rule? So how can I guess how many parameters in this case without like, I have 5 variables.
If they're all independent, can't you just multiply however many you have?
And last time the rule we are seeing is.
Sorry, what'd you ask?
So if we are going to treat all these cases, how many cases we will end up finding? Like B is true, E is true, A is true, all of them are true. Next, I am going to consider that B is false, the rest is true, until I will be coming to a setting where none of them is true. So it's, yes?
2 power n minus 1.
Yes, 2 power n, n is the number of variables that I have here, minus 1. And why we do the minus 1 here? Because there will be extra points. I didn't say this last time, but if someone will be that smart and will guess why we do not consider like only 2 power like only n, why we are like performing this minus 1, there will be really extra points for this person.
I mean, I have a guess. It's probably not right.
I mean, I have the answer, but I'm just a little confused.
1 second. Okay.
We are starting from P of 0. We ended at 0, we are using minus 1.
If you can explain more.
Yeah, there are the T1 parameters, right? We are starting from P of 0 to P of 32. To enter that index, we are using that minus 1.
Not really. No, it's not about the index. It's about the fact. There is a fact. Yes, Zoya?
My guess is that if you were to multiply it like 2 to the 5, that would be counting your initial one that you're starting with in the list, and you don't want to loop back around and like get to the same endpoint. You don't want to count that first one, right? Because otherwise you want one unique parameter every single time, right?
Yeah, every single time there is one parameter. This is one parameter, this is the second one, and at the end I'm not considering this one. Why?
Because that's just the opposite of the other one.
Because we have the negation and we have P of A and P of not.
I think we are expecting something to happen.
No.
I think we are expecting something to happen in all cases.
Gotcha.
No, you will, yeah?
Yes,
Dallas.
it's so you can find the last parameter.
You got it or not? So if I have knowledge about the probability, like in the start, I don't know anything, and I want to guess all these probabilities. I'm taking the first step. This is becoming a fact. I am computing this. Then I am performing one negation, I'm also computing. Until the last step, I'm computing all of them. One of them I'm not computing. Why? I don't need one more parameter. Because I have this fact that the sum is equal to 1. So if I am going to have 1 minus whatever I am computing before, I will get this one. So there is no need to complicate the computation of the number of parameters, as at the end there is one parameter that we can obligatory deduct if we have the previous parameters and we know that the sum is equal to 1. Okay? Okay. So you will not forget this forever. So is that clear, Zoya?
Yeah, that makes sense now. Thank you.
Okay, for all the online guys, so is it clear?
I mean, not immediately, but if if you just give me some time, I might figure it out as we go through.
Okay, no worries. So what we have here, okay, let's move to the second example. Here there is no -1 because what? Because we are not going to check the multiple like possibilities, or I have B and the other scenario is not B. Okay, so the how many parameters I have? Only one. The second one I can deduct. Okay, if I know B and then the not B, I would say 1 minus the probability of B, then I will get. Okay, so each time now I have probability of E. How much is the number of parameters here? It's same as B, it's 1. And for A, given B and E now, the number of parameters here is you are going to treat each particular case. You are A given B and E. One time we are going to consider not B and E, then we are going to consider B and not E, and then not B, not E. So if I manually compute all this, it's 4 parameters. But how I would consider this, it's 2 power, B and E are 2. So it's 2 power 2, which is given 4. Is that clear? So we go to this example now. Here, I have only one case. If I know it, then I can guess the opposite or the complement for that. So I have how many parameters here? 1. Which one? P of M given A. So for this one, I have 1. For this one, G given A, I have 1. Okay? 1. Is that clear?
I thought there were 2 parameters because like it can be either A or not A, and in either case.
Yeah, you are right. This is one. So is there any rule that you can extract from this slide? What is the difference between the probability of B, that here I'm saying it's 1 parameter, and the probability of M given A, I'm saying it's not 1 parameter, it's 2 parameters. So
Because it's independent versus dependent variable.
are you getting that? So here, if I have the B, it's independent. So I have the B and I can guess the not B. 1 minus B I will get. But here, each time I would consider, like it's mentioned here, if M is there or M is not there. And if A is there or A means true or false. Is that clear? So
Yeah,
we are going to enjoy a lot with these examples. Jeremy, is that clear for you, please?
For that section it is, but I was curious why the probability of A given B and E, got this thing hovering over so I can't see the bottom of it. Whatever the number of parameters down there, I think it's supposed to be.
Not A.
Yep.
So it's
So-
clear?
Well, I'm trying to see why it's not 2 to the 3 minus 1.
Not 3.
Yeah, that's why I'm trying to figure out why it's not 3, because you got A and not A, B and not B, and E and not E. It feels like all of those should add up to 3.
Getting it?
No, but
No,
I'll try again later.
You know,
No, we will not move.
Okay.
If someone is not getting, we don't move. You know my habit.
Yeah, no, he brought up a good point. What I think is kind of my understanding is that you can have an alarm or not an alarm. So that would add an extra, extra.
No, but you have an alarm, okay? And both B and E are there. If you know this, then you know the probability of not having the alarm when B and E are there, which is 1 minus the probability that you know in the
That's what we were
start.
just talking about. Yeah.
So here, each time we are removing 1, and this is why we end up by 4 parameters.
Removing one because we can
We
extrapolate.
can guess it. If I have this one, the complementary for this one is this one. So it's not like this one, I need to have all of them to guess 1, and I'm reducing only 1 parameter. Here, from each given one, I can guess 1. So given 8 parameters, 4 of them, each time I could be able to guess, and then I have only 4 parameters.
Okay, so you're able to guess or whatever for each line rather than for the whole thing.
Mhm.
So that's why we're taking 2 to the fourth minus 4, not minus 1.
Yeah,
Or 2
you
to,
can
to the
say
third
that,
minus 4, sorry. 2 to the third minus 4. Okay.
which is 2 over 2.
Yeah.
Okay.
Yep. Cool.
Okay, so for everyone, it's clear.
So you
Okay.
don't count the complements, right?
Yes, because the
Okay.
complements are parameters. If I would be counting and I have already the information, it would be costing me like it would making the complexity more, and it's useless because I know that. So what we do is that if I have knowledge about something, there is no need to compute and no need to consider as a parameter.
Yeah,
We
makes
will
sense.
have more examples, and I'm sure that you guys will enjoy. So in this case, this is a case of the complex like Bayesian network. And what we end up having here, if I want to compute the joint probability, which is the probability of B and E and A and M and J, it's equal to the probability of B times probability of E times probability of A given B and E times the probability of M given A times probability of J given A. And until here, this is extremely simple because I'm just translating the graph that I have already here. Okay, this everyone is okay with that. Now, the second step is that if I want to compute the how many like parameters I have, probability parameters, I'm going to compute this is equal to 2 power 5 minus 1 given the joint probabilities. If I'm going to apply here, I have 5 variables, and this is what we seen last time. If I'm going to have 5 like variables, I'm going to have 2 power n if n variables minus 1. This is clear for everyone. Now, if we are going to compute the same thing, given this formula that we are getting. So here, if B, I have only one parameter. We are clear how we compute that. For E, probability of E, I also have one parameter. Probability of A given B and E, I have 4. And the probability of M given A, I have 2. Probability of J given A, I have 2. So if I am going to compute the parameters for all this part on the right, so it's going to be the sum of all this. So the sum of all this would give me 10. And if I am having the same thing, expressing that using like the Bayesian network is going to give me like 10 parameters. If I am only using the joint probability, I'm not that we were like studying last time, I'm going to have 31 parameters. So this only could show how efficient and compact are the Bayesian network. And from here, you may understand why, like, and how researchers are based on this for many problems, whether you can cite, for example, in deep learning for like, if you have a huge space and you are getting like having an optimization problem, so you can use in different settings, in different domains. And this is the main reason why is that these like networks are too much powerful because they reduce the number of parameters. They are extremely efficient and compact. Is that clear? And so this is why, so it's because we are using these networks, encoding dependencies only where they are necessary. So if I have unnecessary dependencies, I won't consider that. Here if you can see in the formula, we each time considering for the graph, I have A depending, for example, from which elements given the graph. I am not going to consider A and all the rest, okay? So this reduces the number of parameters and the total number of parameters. And this is why, as I was mentioning, the Bayesian networks are compact and efficient, just like for representing the joint distributions of complex domains. So is this slide clear? So this is the key for entering or starting, like highlighting the importance of the Bayesian networks. So is that clear for everyone online?
Yep.
Okay.
I'm curious, is that
Yep.
reduction in 21 based solely on not calculating the complement or not having the parameter of the complement in there?
So
So
we
if we go
can
back,
guess your question if we come back to this slide. Yes,
yeah,
you can
so
ask based on these variables. Yeah.
we're subtracting 1 from the first one, we're subtracting 4 from the third one, probably 1 from the second one, and two from the last one. and it's not 21. So I'm trying to figure out where that comes from.
Oh, I think I know why. It's because we're assuming some dependencies on the right side of the equation. So like A given B and E, for instance, and then you have, those 4 parameters. Whereas the 31 parameters assume every single one is independent. So there's, not one, then not the other, then not the other, and you have to do every single combination, if that makes sense.
Yeah,
Yes.
so assuming that they are all independent on the left is another reason why we're having so many extra.
Yes, you're right.
Okay, cool.
Great.
Thanks, Zoya.
Thank you, Zoya.
I have one more question, actually.
Yeah.
Why do we start with 2 to the power of 5? Is it because the probability of yes and probability of no? So there's 2 outcomes
2 here.
for John or Mary.
For the computation of the total number of parameters, you mean?
Right.
So here we're applying the rule. If you have only 2 parameters, A and B, you try to guess, or 3. So if you are having, like the truth table we make, and to guess how many rows you are going to have in your truth table, we do 2 powers how many variables you have. And here the number of variables is 5. So put 2 power 5 is giving this. And thanks to you, we are understanding why we are doing -1. So this is giving the total number of parameters. If I would have, it's a general rule.
Just always starts with 2, general rule.
2, yeah.
Gotcha.
Because
Yep.
each element is taking yes or no.
Yep.
It's a binary.
Yep.
Okay.
Yeah. I was just wondering where the 2 was coming from. That makes
Okay,
sense.
because it's binary,
This
true or
is
false for
binary.
each element. This is how you do your truth table all the time.
Yep.
Okay, so everyone it's clear for everyone? Online? Okay, great. Now, so we are understanding the importance of these Bayesian networks. We are understanding each time how to compute in the case we are considering these dependencies, or if we consider on the right, like Zoe was explaining, sometimes it's independent, how to find the total number of parameter as compared to when we think of the whole possible scenarios, okay? Now we are going to have one quiz. Let me just publish this and to confirm that everyone is understanding well. Last I'm going to say something here. When I make quizzes in the classroom, please don't worry. I understand that if, for example, I'm asking, like last time in the quiz, I was asking, I'm guiding you. I say, for example, sometimes give me the whole formula without any spaces and including the final result. I give you some format to follow, okay? And in another one, I was mentioning just give me the final result. So this all is just training for the final exam, because if all the quizzes, if you can remark, it's just maximum you find 1 point. Each element would be 0.25. So it's extremely less points. If, for example, someone is getting extra points, you may get 10 points. I would add that at the end. I don't want to make you lazy now. So all that is just for you to learn. It's not to reduce your final grades. So don't worry about that. But for the exam, if you are learning this and you are going to read really well, then we will not face any problems, because now I was in some cases opening the quizzes for some students who were asking from me that. I was I try to help as much as I can, but in the exam, I am clear with everyone. I will also announce that it's your responsibility to read and understand and answer with the accurate format. I'm not going to help anyone in the exam. For this and even whatever exam, we will be having extra points that may cover these misunderstandings or mistakes that you may commit, okay? So you are going to find this right now in the classroom.
So I do want to ask, are we searching for the probability parameters assuming they're all independent like before, or are we doing the dependency as well, so there's less of them?
No, here I'm mentioning it's like this. What you can see in the screen, Zoya, you have the probability of this and this and this and this. Okay,
So we'd use the first formula, right?
Okay, let's see. Where is it? The quiz. This one is mentioned. General Bayesian network, I guess. 1 second. Let me. Not this one. Okay. Not this one. I avoid publishing all quizzes one time because even for the asynchronous students, when they are following, like they try not to, like one by one. So you can start guessing about the probability in each case if you want, Zoya. So we will not have this as a quiz. Sorry for that, but let's do it together. Yes. Done. So the same we did before.
Sorry, is this quiz supposed to be showing up?
We are done. They said they're done. You are still checking in the canvas, Jeremy?
Yeah, I thought we were waiting
No.
for that.
Oh, sorry. I was just mentioning that we try to guess without like checking on canvas. We are going to answer together.
Oh, okay.
So try to guess.
Just the first part still, or the stuff in purple?
You try to write it. So you have here a different diagram.
Oh, I see. I'm
So
sitting here going,
try to
I already
guess
got
which
my
are
one
your
number.
variables. This
Okay.
like element is equivalent to which expression, and try to for this one to come up like Zoya is saying the total number of parameters. Try for this one also to conclude the total number of parameters, and then try to compare as we always do.
Gotcha.
It's the same thing we were doing before. Exactly the same thing. I always encourage using a pen and paper. What was your name?
Sambar.
Sambar. So did you write the expression on the right?
Yeah.
Oh, great.
So I'm a little confused about the one on the right because I'm getting a number that's really close, but not the same.
Ah, you're checking
Oh.
the solution. Okay, we'll
Yeah.
discuss that together. So the rule says if we have the joint like A and B and C and D and, like in the left side. The number of parameters is 2 power n, which is n and, minus 1. And we're clear why this minus 1. If I have the probability of A, for example, which is independent from anything, so the number of parameter is 1. One we know, and the other one that we can guess, so the number of parameter is 1. Now, if I have, like, for example, a conditional probability, the probability of A given, let's say B, for example, 1, only one element is given. So here we consider 2 power n, which is 2 power 1, which is 2. If in the right side I may have 4 parameters, I say A given 4 parameters, okay? A, B, C, D, or for sure A not. So what I'm going to consider 2 power 4, the number of conditions, okay? So this is the key. Are you done? Okay. How much you are finding for the left side? Now it's A and B and C and.
157.
Okay, that's correct. Online. Zoya, this is your finding exact?
So I am close actually. I think I figured out where I was wrong. I was getting 17 on the right side. and I know
No,
that's
we're
not
still
right.
not discussing the right side. On the
Oh,
left
gotcha.
side, you are finding 1,
Oh,
2,
yeah, yeah.
7, 127.
Yeah, 127.
Okay, that's great. Now let's discuss the right side. So how much you are finding for the right side, the number of parameters?
19.
19, that's correct. So let's see together why. So on the right side, we know that how many parameters I have, A and B and C and D and E and F and E. So it's how many? It's 7. So it is 2 power 7 minus 1, which is going to give 127, 127. For the second, the right side, sorry, what we have? Probability of A, we have only 1. Probability of B is the same, we have only 1. C, also same. Now, we have a conditional 1 here. Conditional 1 is, we have condition, the condition is given 3 parameters. So how to compute this? It's 2 power 3, which gives 8. The same for the second one, only 1, so 2 power 1 is given 1. And same here and 4 here. So the sum of all this is 127, and the sum of all this is 19. Okay, so I'm really proud of you. Okay, so next now let's consider this case. If I would let you compute all this, so what will happen? You're going to find yourself with a huge number of parameters. So this example last time we also see where I started talking about uncertainty, and I told you I'm not the car expert. So, but imagine someone who wants to know if something is happening, why, and why. I ask the reason for that, why is happening. So if my car won't start, I may consider this whole space for each case. For example, like the battery is flat, why? It could be this. This is also generating other possibilities. Or so here we have, even that it seems not that much complex example, but given the number of parameters, we can guess like it's extremely like complex one. So here we have 16 parameters or random variables, okay? And if we are going to compute this like joint probability without using the Bayesian network, we are going to find, if we use the same rule that we always use, it's 2 power n minus 1. The n in this case, it's how many like variable do I have? So if I have 16, 2 power 16 minus 1, it's equal to, how much? 65k something which is not less, like half k. So this is a huge number of parameters. And imagine that we are not dealing with the real world, like a more complex scenario. So this is the quiz for the case of car diagnosis, but let's like see together how we are finding this. The probability of battery age here is independent from anything. So this is why it's just 1. Same for this one and this one, it's equal to 1 because there is no input for, we don't see any other variables influencing this one or a conditional probability. Then this one, the battery dead, for example, we are going to consider in the case like conditional with 1. Well, that one itself could be yes or no. So here we have 2. And in these conditional examples, we say that the rule for computing, it's 2 power n. So the n is equal to 1, and I have only 2. Here also you would be able, your n in this case is equal to 2. So this is why you are going to have 4 here. And same, it's increasing until we are getting this, like, the car won't like work, we are reaching to 32, and like, it's really complicated exam, okay? So this is reduced, if we sum up all that, to 63 with the Bayesian network. So you can see the huge, like, decrease, okay? We are now clear, at least. Okay, you can take 5 minutes rest. If we are clear with this, we deserve 5 minutes rest because the upcoming part needs more concentration.
Oh, dumb question real quick. I think I misread the announcement. What day is the exam gonna be on? Is that like opening the 2nd or opening the 9th?
Let me check the calendar. Check. This, the second, which day?
October.
Oh,
So like this Wednesday
Okay.
versus next Wednesday.
1 second. What we said last time, we said that there is a makeup session we are going to consider for the exam like session. To not keep checking if you guys are busy, some are getting courses different from what others are getting, and so on. So for the next Wednesday 2nd, which was supposed to be the exam, we are going to have the review for the exam plus Zoya's presentation. I was mentioning that you are going to enjoy your weekend. Also, maybe if you want to revise whatever we are going to review on Wednesday, and the exam is going to be open on Monday, working day. So Dallas was asking for 4 days, asking for 2 days. I said I will give 4 days. So the exam is going to be open from next Monday, 7th, like 4 days, until next, like, Thursday, 10th of October.
Okay, awesome. Thank you.
4 days, but if you are going to open, like, you have the right to open it only one time and complete it, like, it will be like 1 hour or 45 minutes. And if you are going to complete, then you are not going to ask, like, I misunderstood one question, or by mistake something is happening or something. So we are training from the quizzes that we need to really read well which format we are going to input the result. If any problems, don't worry, because there will be always extra points, but I want you to do your best. Okay.
So I don't want to deny you your 5-minute break, but the right side of that probability of A through G, I got a different answer.
Which one? In the
So-
same slide of curve diagnosis?
Just back a few.
This one?
Yeah.
Sorry.
So
Yeah.
I was trying to figure out why the probability of D given A, B, C wasn't having a subtraction of, so 2 cubed, why wasn't it 2 cubed minus 3?
The n here, it's 3 elements. So we
Mhm.
are having 2 times 3, which is equal to 8.
Right, but why aren't we taking the complements out? Like we did before in the previous example.
We always take the complements out because if something we know, there is no need to complicate things and consider it as one parameter. This is what we were explaining right here. Let's go back to that slide. I think Zoya was explaining this.
Yeah, but we didn't seem to take it out of the 2 cubed one.
If here you are having 4 parameters, this was clear for you, Jeremy? Why we had 2 parameters here?
Yeah, I mean, I see the
Excuse
2.
me, 4 means I have 2 variables, conditional, and I have a total of 4 parameters. This was clear for you?
I guess maybe not now that I look at it again, because I thought A was part of it, and then we subtracted 2 cubed, which was 8, minus 4, so 1 for each line. So maybe I was misunderstanding that before.
Okay, so I understand that this one is clear for, it's not clear for you now. I
Yeah.
will re-explain this. So I have the probability of A given B and E. Now what we will do, I'm not certain, I'm not sure about what values that A can take, B can take, or E can take. So what I would consider, I am going to consider that A is true. So this is why you will see here, I am checking the probability of A given something. But here it's always A. A is happening, okay? So that thing now, this is what I'm going to consider within a truth table. And Dallas was asking me here why we consider the number 2. You remember? I say 2 because each element, if I have A, B, C, D, E, it could take 2 possible values. For B, for example, it could take B, which is true, okay? And it also could take not B, which is false, okay? So in this case, you have B and E. B is taking like B and not B, true or false. Also, E could be taking true or false. And it means I could consider E and also not E. Okay? So in this case, me, each time I have my B and E, so both of them are true, then the combination that I can detect from these like elements. From this, I can take combine B with E, B with not E, not B with E, and not B with not E. So if I would consider in the start that A is always true, so it would take me to 4 possible combinations, possibilities. So A given B and E, A given not B and E, A given B and not E, A given not B and not E. So now if I have all this, and I know that, so if you suppose that this is your whole space, okay? We were studying the complementary. So this is your omega, or let me denote it by something like this. There is 2 possible events, and for each of them, it is going to be the sum of probabilities, P1 plus P2, how much? 1. Okay, so if I have my P1, it's B, and my P2, it's not B. There are 2 complementary probabilities. So if I sum B and not B1, the probabilities all the time is going to be 1. If by finding this first part that, oh, sorry. Okay, so this first part, Jeremy, I know that you were focused with me. This one that I was discussing right now, okay, is taking 4 possibilities given A is true. Okay, so this is A given something. So I am going to have this as P1.
Okay, so
Now,
it's the whole complement of A being true, and then the
yeah,
combination of B and not E, E and blah, blah, blah. And that we can calculate that we don't have to take A as another parameter.
case. Yes, you are right. So
Okay.
here, if I have this, it's taking this all space. How can I guess? I have probability of A given B and E. So what if I want to compute the not A given B and E? Here is the
Right.
complementary. So it's 1 minus this one. I compute 1 minus what is remaining. Okay? So
Yep.
this is the concept. And this is why, to keep it as a general rule, if I have 2 elements, how to find all possible like combinations, it's 2 always, because each of them is going to have true, false, means 2 possible values, binary. And how many variables I have? It's 2, so it's 2 power 2, which is equal to 4.
Okay.
And the complementary is I'm considering for each like case. This is why it doesn't show here, but we are explaining. So for the case that we were there, it was how many elements? It was 4. So it's same 2 times 2. No, this one, not this one you were asking about. This one.
Yeah.
So how many elements I have here is 3. So here
Okay.
it's 2 power. How many elements is 3, which is equal to 8.
So
Is that clear?
yes, I was misunderstanding why we or what the subtraction was based off of, and it's actually taking the entire
I got it.
series of A, B, and C and its negation,
Mhm.
and then the complement of not D and then that whole series again.
Yeah, so you
So-
are right about thinking like this. It's a little bit confusing, but it's, I think, now clear.
Okay.
Okay,
I think I'm good. Thank you.
Okay, most welcome. Okay, we're done with 5 minutes. Okay, so, or Jeremy needs 5 minutes.
No,
I
I'm
also
good now.
don't need.
Yeah.
So let's move. We're going through all this. Now, let's take the case of constructing a general Bayesian network. So there is a rule, which is called the product rule. And this rule is going to make things simple. So if I have three n random variables, so how can I illustrate that? For example, I'm going to start with the first one. So here I'm supposed to make it little x, but x1, x2, x3, x4, and I have that much x until I would find how many? We have n, so here you are supposed to find x, n minus 1. Before that, it's n minus 2, okay? Until you are going to reach to xn. So these are random variables, okay? So if I want to find, use the product rule, the probability of x1 and x2 and x3 and until coming to xn is equal to the product from, for all these elements. Each time we are going to take xi for I going from 1 to n. For each of these, we are going to consider 1 given the rest. 1 given the rest. If we start with, for example, the probability of xn, this one, what we have, what this probability of xi given xi minus 1 until reaching all this means x1. Okay, how we can write this? If we are going to, we have the product, so we are just going to consider each element alone, okay? It's like a box and we are going to check. Instead of having the big product here, we are going to check which elements we are multiplying together, okay? So first of all, we have the I is equal to 1. The n is, keep it n, okay? So we are going to take the last one, which is xn, and we are going to consider the multiplication from x n minus 1, x n minus 2, minus 3, let me say I'm reaching to x3, x2, x1, okay? All of them I'm going to multiply together, okay? Now, for the second part, I am going to consider the probability of, now I'm going to reduce the xn, now it's done. I'm going to move to this one, xn minus 1. What I'm going to consider in this case? The rest, which is going to take me in this position what I have. Before xn minus 1, I have xn minus 2. All this information is given from minus 2 up to x1. Then at the end, I'm going to check all these. I'm going to multiply. Each time I am going to reduce 1 and multiply with, given all the rest is given, okay? So at the end, if I am reaching to x2, it's going to be the probability of x2, and what is the rest? It's just x1. So it's probability of x2 given x1. So this is the product rule, which is really simple. So if you are having a set of and by the way, here you have the condition, okay? Conditional means if you are going to show me here the graph, I must have or see somewhere the arrows that are connecting these variables, okay? Which is my independent variable, xn. So I am going to treat it first. This is why I'm starting from here. This is why I'm not starting from x1, because x1 depends from all this. Okay, I start from xn because here there is nothing like input. So this is xn. If I want to compute given all this, so it is the xn given all this, which is given means this and this and this, all previous elements. Then this one is done. So I'm going not to consider because I'm already considering here. So I am going to move one step to the just before, like I have x n minus 1, which is given all the before steps, x n minus 2, and so on. Is that clear? So this is called the like product rule, where if you have a set of elements or variables like from x1 to n, if you are going to compute this using the product rule, so it's the product of all like xi given all the previous variables, from like multiplying that from I varying from 1 to n. And if I am going to open this box, I am going just to illustrate it, which is really simple. Like each time you are considering one variable given all the rest, so you have the conditional probability each time, okay? Until reaching to the last element, you have only like x1, which depends from x2, so the probability of x2 given x1, okay? So is this clear for everyone? So this is called the product rule. Oh, sorry, so we are moving. Okay, so here is the simple case where all of them are like connected like this, which is corresponding to the Bayesian network, this example I was just talking about. This is the Bayesian network. So if we consider this one and this one, which is the Bayesian network, and what is the difference between the two elements? What is the difference between this graph I was explaining right now and this graph? So here we can see this is just an illustration given 5 elements, and there is an additional like thing which makes this like example more complicated than what I was illustrating.
All connected.
Yes, this is what we call
Neural network.
No, example of neural network is called the last part of the network. Fully connected. So we will see later when we talk about the neural networks. So the neural networks, it's a set of neurons. We are going to reach to that. And what we call this, it's one layer, for example. One layer is having many neurons. And in the next layer, I can have other neurons, okay? But the rule says that we call the last part or fully connected because for each layer, every neuron is connected to all neurons from the next layer. Okay? Is that clear? So there are different types of how to illustrate this, different types. So this is an example where we are presenting x1 is connected, not only like here, it's the opposite way. X1 here is connected to all like x's coming after. For x2 also it's connected to all the rest of the elements. For x4 here it's only connected to x5. So if we are going to consider the last variable, it's the variable to which all previous like variables are connected. So we do not have only like in this example only one like depending element I was mentioning. However, here I have multiple, okay? So this is in this case, so we are going to see how to apply the product now rule given this specific example. So I think this one I'm publishing, I'm sure now. Yep, this one is there in the classroom. Okay, let's make it public. General Bayesian network. Try to connect to your classroom. Okay. So in the quiz here, if you are able to connect, it says that October 6th. Are you able to take this quiz? Quiz 3, quiz like a general Bayesian network.
Yep, I see it now.
Just it's not about seeing. Can you take it? I was expecting to be here last week, so I think the until date is 6 October. You're not able.
No,
Okay.
I think I'm able to take it.
Ah, okay, then great. So here, let me first, before taking the quiz, because, okay, it's important, but for me, now the most important than taking the quiz is to read the instructions. So here, what are you requested to do? So you need to fill in the blank with the exact final value. Means I don't need any proof. I just need one single value, okay? You are going to tell me, for example, the total number of parameters for this network is how much, and that is it. So the number of parameters, it always depends on how we are extending the formula. If this formula we are extending using the product rule, so we have this illustration or this example. So this is what you are going to use. So for each element, you are going to consider how many inputs to that, depending from how many variables. Not the simple example like each one is connected only to the previous. Here, each one is connected to all previous.
So can we use the previous rule to calculate this, or do we have to use this one? Because I guess I'm still a little confused about how we use this one.
If I take the example of probability of n here, and n is the last value you have from 1 to 5. It's the same from 1 to n. So here your n is 5. Apply this rule given this graph, okay? So your n here is 5. So here, if you want to check the probability of x equal to 2, it's this. So what we have? The first one, it's not dependent from anything, x1. So x1 here, the number of parameters is how much?
Just one.
Just one. The x2 now is depending only from x1. So the number of parameters for x2 is how much?
2.
2. You are right. No, I won't say. So x3 here depends not only from x2, also x2 and x1.
That one's 4.
Yes. You got it?
Okay, that makes sense. Thank you.
Yes.
Hopefully I can get the quiz done before work. It's going to be tight.
Okay. At least I want to see few quizzes done right now, otherwise you take your time. I don't think that because you are active and you are doing the quiz on time with me, sometimes you are failing if you compare to someone who is going to see the lecture later. Maybe they could see what we are discussing and the correction and get 1. I always consider giving almost the sum of what you can get award from quizzes. It could be your extra points because I understand and at the end you can be fair with everyone. So do your best and don't think of the grading.
All right, I'm going out on a limb here and saying that your answer is wrong.
How much you were mentioning?
Huh?
How much? So are we studying right now any particular rule for computing the number of parameters? We are not. What we are studying is a new rule, how to compute product rule. This is what we're checking. We are not even discussing about the number of parameters. So this is just a simple review of what we have seen so far. And it's not because I'm showing you the network a little bit complex that you will think that whatever we are studying is not valid. Whatever we are studying is still valid. Computing the number of neurons, the probability of something is always given what? And given what is the conditions. And the conditions is what arose I see. It's not because it's fully connected, it's almost fully connected that I can say it's not the same way that we were studying before. Probability of n, the probability of x to give x1. So if you can say x2 is the only one dependent from x1, it's same. I divided in two descriptions. The x1, x2 is the only one dependent from x1. Now, the number of parameters. Two power one. However, in a way, it's going to show that it will go from x1 to 2. هنا it's 1 ولكن it's equal ولا you are going to divide على 0.25 each. Okay, the sum are yes, but which almost is having the same importance. It makes almost the conversion network. We are going to focus on probability to reach to 5. It's more than okay. So it's I don't know, but computing the parameter is yes, that's so. So just clear. We're finding how much it.
Yes, that's my guess.
How much of it? We see the one. Yes. And here, what is the final number?
So we should consider the independent variable.
We didn't join part or we didn't complete parameters.
Welcome.
Okay.
So all of
Include
the same.
yeah.
I still did one. And you? Go. Okay.
Sound.
Yeah, okay. Any questions?
No.
Okay. Yes. Oh, that's great. Excellent. Great. I'm really happy. Online. How is it going?
Well enough. I know, I mean, I know what I did wrong, but I don't understand why I got two different numbers when I followed two different strategies here.
Okay, no worries. So let's explain together. Always don't let anyone confuse you. And this is always my target. Not because I'm bad, because I want you to see things from different perspectives. So at the end, you're becoming the expert of it. Okay. So before we were saying that if I have, let me, okay. If I have here x1, so is it depending from anything? No. So how much is the number of parameter here? It's 1. So it's 1. Then I will move to my x2. In this case, I have my x2 is given x1. So if I have given something, only one thing, so the rule is 2 power, how many things? 1. 2 power 1 is going to be 2. Then I have x3 here. It's going to depend from x2 and x1. How you know this? no matter how your network is complex, just check how many arrows are given as input. So you don't need to make your eyes go far, just how many, 1, 2, and that's enough. No need to check anything else. And so if I have given 2, so the condition is given 2 variables, no matter what are the 2 variables. So the probability is 2 power 2, which is equal to 4. Next, we have 3, yes. So 2 power 3, which is equal to 8. And then we have 5. For x5, we have 4. 2 power 4, which is equal to 16. And we say that if this one parameter, 2 parameter, 4, 8, and 16, if I want to check for all like the variables, I just need to sum up all that, which is going to give me 31. You can do that the way we did, which is 1 plus 2 plus 4 plus 8 plus 16. And you can do it also the same case here. We have how many variables? It's just 5. It's 2 power 5 minus 1. So in both cases, it's giving like 31. Is that clear? Okay. Let's take this example. Let me publish it first. You can start thinking of it right now until I make it accessible for everyone. So here you are going to do the same thing, but taking into consideration that your variables are independent. So you have quiz for Bayesian network for independent variables. What you have, I think you can access this. Yeah. Okay. Try to think of this like individually. Still, guys, we are not reaching the Bayesian networks over time. So we are really moving slowly, but at least I'm happy that everyone is almost understanding things. So I would prefer understanding something rather than going quickly over 2 things. Okay, is this done for everyone now? Are you done? Online? Okay. So how much?
5.
Great job. So here there is no connections. So every like variable is presented by the probability of that one. So which is given one parameter for each, and you have 5 variables. So you are going to have the sum of these 5 like parameters, which is given 5 parameters. So we are going now to move. Like sometimes if you have a Bayesian network, it's a little bit complicated. And if you have more variables, it's too much complex. So there is something what we call the D-separation, which means if you have, for example, nodes connected, and there is one node that is separating the knowledge from the like indirect one influencing the where you are now, okay? So this concept is very simply, we are going just to finish very quickly, don't worry. So D-separation is like a rule. So A and B are D-separated. There is special like conditions to apply this rule. If and only if every indirect path from A to B is blocked. Is blocked means what? Means for A is here, for example, blocked if and only if one or more of the following conditions is true. So here we see the C is the evidence, for example. Going from A to B, we go through C. And here, if there is an evidence variable C on the path, such that, like you see there, this, like C is the evidence. So if from the path from A to B, there is a given evidence, something that you know, means all this is like useless. You can make separation, stop here, and then you stop in this side, okay? Next, there is an evidence variable C on the path such as C. So here, for both paths, there is an like existing variable C, which is the evidence in this case. Or there is here what you can see, they are all like coming to C, and then there is like branches coming from C, okay? So there exists a variable C on the path such that neither it or any of its descendants is an evidence variable, and like here you are going to have these are coming to C and these are coming from C, okay? So these are simple rules. If you see in the graph the evidence is there, or the evidence is taking you here and there, or the evidence is here, there is input, and then from it there is specific input. Here you can apply the like D-separation. And D-separation, it's like when the path is blocked, and the path is blocked if and only if one of these is like valid. It could be more than one, but if at least one is valid, then we can apply this rule, okay? This rule is simple. What we will do now, if two variables are too separated relative to a set of variables Z in a directed graph, then they are independent, conditional on Z in all probability distributions such a graph can represent. So all that, I'm just presenting the idea, but it will be clear given an example, okay? So this we have seen so far. So how to read this symbol? A is conditionally independent. There is no like relationship. C is conditionally independent from A. In this graph, C is here and A is here. So is C conditionally independent from A? I would give you like some time. Is it true to say that C is conditionally independent from A? So C is dependent from A. How? You are right, but how you got this?
C is dependent on B, B is dependent on A.
Great. So here, given you have C, you can Given B, you can guess C. Okay. Next, C is conditionally independent from A given B now. A given B is this one. Are they independent? So it's true. They are independent. Why? Because if I already know B, given B is there. So this is the one straight like connected to C. So here we can say that A is conditionally independent from A given B. Okay? So given B, B is there. So B is there. So what is the U? So this is independent. So this is true that they are independent. Okay? You are going always to ask yourself dependent or not dependent. But this symbol, it is right independent. So when we say true, it means they are independent, which is true. Okay? They are conditionally independent. Now, yes.
If two variables are independent, so they are conditionally independent. It's not the same.
No, conditionally means we are talking about the given.
Yeah.
And we can have a set of given things. It depends on the representation on the graph. You can see that. Okay, so now what we have? We have C is conditionally independent from D. Now, is that true?
Yeah.
Dependent or independent?
Independent.
Who is saying dependent? C is conditionally independent from D. You can say yes or no based on the rules we have seen so far. So is there here a path direct from like between both C and D or not? So they are dependent. A is there. So it's false. They are conditionally independent. Okay? So the next one, C is conditionally independent from D given A now. C is conditionally independent from D given A. D given A is this one, and C.
Oh,
What we have?
it's dependent.
It's true. It's independent. But why? What is the common here? Who is the common parent of both A and C? It's D. So A here is blocking any information between C and D. So they are conditionally independent. That's true. Okay. Next, no, let's check with this one and here. So C is conditionally independent from E, sorry, is conditionally independent from C and D. Always think if there is something which is in common blocking that, then it's true that they are independent. If nothing is blocking the road, then they are like dependent. So here, what is blocking the road between like E and C? It's D. There is no A here. We have E, C, and D. You always check the variables that are in your formula. So if you want between E and C, D is blocking the row. So it's given. So the saying that E conditionally independent from C and D is they are independent.
Yeah.
It's true. Yes. Okay. So just a direct application of the rules that we see so far. I can keep you with this quiz. This is the last thing for today. You can do it at home if you want. And what we are going, oops. So the first one is true for everyone. Let me exit. Okay, that is it. So for the next time, we are going to take pause from Bayesian networks. we are going to check for our review. We have our presentation for fuzzy logics, and later in the semester we can come back to this part. Okay? So any questions? Okay, then I think that we are done for today. Okay, let me stop recording.